Okay, for the second part of the end-to-end machine learning project, we're going to looking at how we can select and train a model. Keep in mind this step is after you have prepared and cleaned the data at the first part of the videos. Now that assume that you already have a data prepared for your machine learning model. So here we go. First step to start is we're going to start by something that we have learned previously. It's a straightforward approach of linear regressions, a statistical method. So in order to do that, you're going to import linear regression from the linear model, create a linreg object from linear regression, and then after that, use the fit function to fit your data, which is housing prepare, and also feeding the label. So we know the housing median value of each house. So you run that, you're going to create a linear regression object. The next thing, you want to try the full processing pipeline on a few training instances. So for example, you can extract a few instances from your training set using index location. So you can extract some data here from the housing data set, which is the unprocessed data set. So we're going to pretend that we get a new data set come in from the housing, and then index location, and you might be able to see these Python index from, this means from 0 to 4. 5 never really touched, so the 0 index to the 4th index. You do the same with some label so that you can get the label from the first label to the 5th label. And to clean the data, we can use the pipeline that we built in the first video. So full pipeline, do the transformation, feeding some data in, and now you have some data prepared. So notice you only need to use transform instead of fit transform, because you're not trying to learn any parameter. That's part of the training, that's a cleaning data process. Now, from after you learn all the parameters like the median and different features, you now only need to use the transform function. So here we are, a transform function. And after that, we got some of these data prepared, and now we're ready to run a prediction functions on the data. So our linreg object dot predict, passing some data prepared. And so we're going to return some predictions. So prediction of the 5 example that we see previously. See that these are the price that is predicted. And we can actually compare that against the actual value. So actual value of some label. So you have also the 5 value that provided from the label of the data set. So see how close these are. So these 210K, this is 286K. 317 change, 340. So you can see they are not exactly satisfied just yet. So you can quickly see that, okay, we do have some marginal errors here, but let's be more concrete, right? And again, before we move on, to want to quickly point out the data prepared is going to look like a NumPy arrays here, and you know you get the right data because look at it. This is the one-hot encoder, right? The last 5 features, one-hot encoder. So that's just some trained data. But typically, you can't just look at by eyeball and see how big the error is. You actually have to have some metric. So the metric we use here is the mean square error. So, and to evaluate it after you got the prediction, you pass it in at prediction, and then you build a linear regression MSE using the mean square error, passing the actual label and the prediction, and taking square root. That would give you the RMSE of this model. And the RMSE here is roughly 68,000. So, well, that's better than nothing. But if you're looking at the median house value range from 120 to 265,000, typical errors of 68,000 is not very great. So this is possible that the model is too simple and overfit the data. Well, this can happen when the features are not provide enough information, and maybe the models are not powerful enough. There is other type of errors here that you can see. These called the mean absolute errors, and the way they compute is slightly different. They didn't use the square. This is just absolute error, and then take the means of that, and then you can figure it out as well. And this is more or less closer to the actual error that you would see. So you can expect to have off by about $49,000 prediction from this model. Okay, so linear regressions, we should try a different machine learning models then, and we can try to use the decision tree regressor. And that's a very powerful model. We will learn about it later on the semester on chapter 6. But the code that you use is quite similar to the linear regression. So you from the scikit-learn.tree, you import the decision tree regressor, you assign the random state because there is some randomness in the tree, and you use the fit function to fit the data or to learn the parameters of this model. So fitting housing prepare, housing label, give you back the tree regression object. You can then use it to predict with house. You passing what housing repair is our training data, and you want to see how well it does. And then you use same things, mean square errors before taking square root and so on. And you take in RMSE of 0. And you might be like, wait, what? No error at all? The tree model really have absolutely perfect? Well, of course, that is more likely that this tree model is overfit the data pretty badly. But we kind of not feeding the data correctly because you typically don't feed the training data to try to predict, because you know, it's just you don't really have a good measure of your performance if you're feeding training data. You had to feed the unseen data before. And of course, you don't want to touch your holdout test set either, because you want to save that toward the end after you build your model. So the way you can approach this is to use cross validation. Right? So I'll let you quickly read this cross validation feature on scikit-learn. And you can see here, this is a great way for you to evaluate and learn the hyperparameter of the model, that you can use your train set to split it into a train and validation set, and using cross validation, great way to do it. And this also give you this prediction 10 times. So you take an average performance over those 10 times, it become more robust. So we use cross-val score, and we pass in our model, which is the tree regression model, our data, our label. The scoring will be negative mean square errors. And the reason negative is that this cross-validation score function would use the utility of a model, which is the opposite of the loss error. So usually you take in the negative loss error would be the utility score. And CV here is called cross-validation, and you use tenfold. So they divide the model into 10 different parts, train using 9 parts, and then validate using the last part. And then rotate the validation to different parts within the 10, so you will have 10 different scores. And then your RMSE score going to be, again, is the square root of a you put negative here because you have negative mean square error, and negative, and then you get back the mean square error. Okay. And then you can display the score in this format. Score means standard deviations, and the score will give you 10 different scores. So a score of 70,000, 66. So each of these are the RMSE of a different fold. So we have 10 of these. And also you see the means of the 10-fold, which is 71,000, with standard deviation about 2,400. So is that good or bad, right? So mean cross validation of 71,000. Let's do the same with the linear regression. Right? So do cross validation with the linear regression model, same thing. and display the score. So the mean average for linear regression is 69,000. So linear regressions perform, in this case, perform even better than decision tree because decision tree have badly overfit the data. So you can try to tune the performance, later. We're going to cover that a little bit. But next, let's try to apply another regression model. It's called the random forest regressor. We're going to cover it later on in the course. For now, you kind of just want to know it is the very powerful model for ensemble learning. And we'll skip most of the details here. One parameter to keep in mind is the number of estimator. So this is just specify how many trees you want to grow in the forest. And if you don't know what it is, don't worry about it. We can just call fit again, and then predict, and then do our ritual by now, mean square error. And you got the RMSA of $18,000. Wow, so that's actually not that bad, right? So again, to avoid overfitting, because you're feeding the training data in, you use cross validation, right? So same code, and the cross validation turned out to be about 50,000 in the mean score. So that's slightly better than the 69,000 and 71,000 for other regression model. So yeah, that's pretty promising. The next steps is that after we know this is model perform better, we can further improve the performance of this random forest model by going to step 6, which is fine-tune your model. All right. So here we know that the random forest perform pretty good, but there is way you can actually tune the model so that it will perform even better. So because this random forest model is having multiple hyperparameters in which you can tune and set certain settings that perform better than the others. So there's several strategy for you to do that. One popular strategy we're using called grid search cross validation, or grid search CV, and you can import it from model selection of scikit-learn. And for grid search, you're gonna feed it with a grid of parameters. So for example, here the random forests have n estimator at the parameters. So here you try different combination of n estimator and max feature. So max feature is the total max number of feature each decision tree can have. Don't worry about the details for now. Just knowing that this is different hyperparameter that the random forest regressor can take. So n estimator, you have 3 choices, max feature 4 choices, so combination of them would be 12. And then you can actually try different combination of different features. So this one right here, having bootstrap, so another parameter for random forest called bootstrap. And this is something to do with whether you do bagging or pasting. You'll know that later on, but that's the Boolean, you set for true. This case you set into false, so that one setting, this you have 2 other setting and 3 other setting. So the total combination is 1 times 2 times 3, which is 6. So for this parameter grid, you're gonna have to run it using grid search CV. Again, you pass in the model and the parameter grid, and then the number of fold you like to run. So this case, you only use 5-fold instead of 10-fold, because we probably want to cut the number of run down a little bit. So we run 5-fold. How many number of round of training do you think we need to run? Right, so we should do some math here. 12 here plus 6 is 18. That's for 1-fold. So for 5-fold, it'd be total of 18 times 5. That's 90 round of training. Right? So that's quite a lot. So it would take a bit of time to run. So you step away for a while. Of course, I'm not going to run it here, but it will take a while to run, and it returns the grid search. And then you can when you trying to fit the data, that's when it's the training. And the nice thing about grid search is it know what is the best parameter for you. So that's typically a good way to approach this, is to set grid search so that you can get the best parameter possible. And in this case, after all the search, it find that for this hyperparameter setting, will be the best results. And by the way, I forgot to mention, the scoring will be the same as you have before. So, and also you want to save the training score, so that's when you set it to true. But the scoring still RMSE, or negative mean square errors. Okay, so then you can also have other attribute like best estimator, so you know what is the best model that return the best result. Okay, so what if I want to see the scoring of all the parameters? So you can use these cross validation result to see it, and then you can combine it using a zip function here. Combine the test score with the parameter setting, or in this case, hyperparameter setting. So you down here, you can see that 49 is the best errors you can get under this parameter setting. Okay, you can see other results, not really important, so we're gonna skip that. One problem with the grid search approach is that you had to try all kind of combination. So it's fine when you have small number of small search space, but if say your search space is great, like you have many hyperparameters and each of the hyperparameters have a pretty wide range, it's better for you to use random search cross validation instead. And the nice thing about random search is that instead of trying all possible combination, it would evaluate some random combination at each iteration, and you can specify how many iteration you like to run. So it's more flexible, and if you have like limited computing power, you can specify how many iteration you would like to run this random search. So that's somewhat helpful. Again, instead of parameter grid, you would specify the random initialization, the range of each of the parameters, and then you will start the randomized search cross validation. Everything else pretty much the same. Here I run about 10 iteration and so 10 and 5 cross validation will be 50 round of training. And so again, you can use random search .fit and show the results here. Out of all these 10 run, seem like 49,000 is the smallest error. And here is the feature. So you kind of see a different parameter setting compared to what you see up here, right? So maximum feature 7, estimated 180 compared to grid search. Maximum feature 8, number estimated 30. So there is maybe local minimum there. This would look like it have a smaller errors rate, so that may be a better setting, even though they really close, right? They only a few $100 different. Okay, you can also look at what features are affecting your model. So this is a linear model, so it takes combinations of different features. So sometimes you want to see, okay, I want to see what features are more important than the other. The process called the feature importance. And so you can actually do that here as well. You can display the feature important of the best estimator under the grid search. Right? So we use grid search, and we can use randomized search here as well. And you can display, it's display, but this is kind of hard to see. You don't know what feature associated with these numbers. So what you can do is you can also build a number corresponding value. So these are just you added the feature that you built, and also the category for the one hot encoder. Kind of stack them together, and so you put it with the feature important and the attribute. You can see each of the important associated with an attribute here, and you see no surprise there. Median income is the most important factor in this regression model. It kind of makes sense. We actually see median income at highly correlated with the median house value, and that probably has something to do with that. The next one is whether it's a inland or not. And this is kind of surprising. So this is very strong features, whether England. So you can see that houses in England typically cost less, right? So it gives a good predictor of the house. And then population per household, longitude, latitude, which is the location of the house. So on and so forth. So we can see number important from most important to least important. So after tweaking your model for a while, you think that, okay, we got a pretty decent set of hyperparameter. Our model is ready, so we're gonna evaluate one last time the final model on the test set. So we're gonna look at the test set now, right? So extract the test sets, and also the Y is the label of the test set. So the test set will contain every feature except the median house value, because we're going to use that median house value for the label, right? Again, you feed the test set through the full pipeline with the transformation using the transform function to get the test set prepared, and then you can use you don't have to train again, right? Because your model already done. So you use the final model, which is what you have up here somewhere, I think. Where is your final model? Right here, right? The best estimator, sorry. Look all the way up here, it's actually right here. A final model, best estimator from the research that we have. So then predict it, and then using mean square error to calculate the errors. So final RMSE, voila, 47,730. You can actually predict down to the cent, but I don't know, that's the errors. So we opt by 47,000, which is, I mean, it's very objective. If you try on the absolute mean square errors, absolute mean absolute error, I'm sorry, then you can see it might be a little bit smaller, probably down smaller than this. But when this URMS is here, right? Even though you know that's a mean square error, so it's not exactly corresponding to the difference between the actual value and the predictive value, and mean absolute error is more, I guess, human readable than this. But, so we off by that much. We can use some statistics to compute the 95% confidence interval, the RMSE, and then you come up with the range. So most of the time your error will not fall between 45 and 49,000. So let's give a little bit of a statistical significance there. Okay, so that's step number 6, fine-tune your parameters. The next step, we're going to go back to the slide to show how you can present your solution, like presenting your solution. So yeah, you get the error getting smaller after each step, so you might feel pretty good about yourself. You'll be able to get the errors RMSE down from 71K down to 69 through each step, so it go down to 47,000, which is great. The next step is to, as a data scientist at the investment firm, you want to analyze, the market, and then you want to make a very nice presentation showing, visual aids and easy to understand statement. Remember who your stakeholder is. So you want to be highlighting what you learned, right? What is working, what is not, what assumption did you make, and some of the limitation of the system. And probably, since you got a great review from the stakeholder, you're gonna proceed to building the system and so on and so forth. But at this step, you don't really bug them down with a lot of nitty-gritty detail of the coding, but rather show what the system can do, and perhaps do a demonstration on the prototype. Okay, step number 8 is launching and maintaining. So you say that you get approval to launch the systems. What else? Like what do you have to do from here now that you have the model and everything? And you get model for the prediction production. You're gonna polish the code, write documentation, and testing a little bit more. And now you can deploy your model. And so there are multiple ways to deploy it. one way to use the Google Cloud AI platform. And the way you can do this is you can save your model using joblib and then upload it to Google Cloud Storage. And then head up to the platform and create a new model version. And then point it to your model. So that's where we give you simple web service. And then you don't have to worry about the load of your system. So basically your model will live in the Google Cloud Storage. And then in the front page, you're going to have some sort of web app. So this is going to basically on the browser. And the user can visit your website, enter some of the feature of the house and hit the prediction. So the real estate agent want to enter all the things and see, well, how much this house really costs. And so your web app right here gonna send. I have some pointer here. Send some input and recommend you can use JSON file to contain the features. And then go to JSON here to the web model. Your model gonna make the prediction using the prediction function and send the data back to the web app to displays on the browser, and then the user will see the predictions. So that's pretty much the pipeline. So you can launch it on the cloud there. We can certainly test it later on if you like to try it. And launching is not the end of the story. There is maintaining that you have to do. You have to update the model over time, maybe to adapt it to the new stream of data that's coming. This can be yearly, weekly, or even daily, right? You also have to continue to evaluate model based on the expert, right? The real estate agent with their experience, they may be able to give you some of the really good prediction of the houses. So you want to incorporate that as part of your label. You make sure you also back up your previous model, because sometimes things go wrong, and then you need to figure out how to back up your model as well. So what did we learn through this tutorial? Also, the first part, second part is you have a really good idea of the 8 steps of the machine learning project. We learned a whole host of tools for data exploration and visualization on Collab using Python. You actually try 3 ML learning algorithms. Some of them, we're gonna pick up later on this semester. So you learn about linear regression. You try decision trees, regressor, and also random forest regressor. You learn how to fine-tune some hyperparameter of a learning method, and you're gonna use this a lot. You want to try the best version, the best parameter setting of a learning method. So that's gonna be useful. So by now you know a lot about machine learning. So my advice going next is keep practicing, try different data set, go online, download different data set, and try them all. And the best way to learn machine learning, I might believe, is to hands-on. Just spend your time exploring different data sets, exploring advanced algorithms, and make sure you're comfortable with the entire process. Right? All right. Great. So we're gonna continue our adventure next week, and by then, I hope you get a chance to, working on your co-authon that we have, and so have fun.